Hello and welcome to the homework help video for this week's homework. Here we're looking at the second problem. If you want to see some tips for solving the first problem in this week's homework, then look at the video before this one. All right, so looking at problem number 2, how do we get started and what should we focus on? Okay, so in this problem, we are given one formula, which is called Newton's synthesis of Kepler's third law. This is a formula that you would use for finding either the orbital period or the radius or semi-major axis of any orbiting body. This formula can also be used to find the unknown mass of a body that's being orbited. For example, if you know the orbital distance and the orbital period of something, then you can calculate the mass of the body that is being orbited. In this case, we know the mass that's being orbited. So let's take a look, in fact, at what we know. So we're told there's a small moon around Jupiter. It's discovered to have a period of 25 days. That's going to be our value of P for period. We also are told the mass of Jupiter, which is important because uppercase M is the mass of Jupiter. We're told it's 1.898 times 10 to the 27 kilograms. And we're also given the gravitational constant, which you could easily look up in important constants, such as Appendix E in your textbook. Okay, and we're asked to find the average distance, so we want to solve for A, okay? And we want it in kilometers. Okay, so really it's just using this one formula. So we're going to have A cubed, okay? That's of course for number 2. And that's going to equal GM over 4 pi squared, okay? And then times P squared. Okay, so remember A is like the radius, called the semi-major axis, all right, applies to any orbit. Okay, orbits are elliptical, all right? So let's think about what we know and whether we have to do any conversions, because we can use this formula as written to solve for A. Okay, so we definitely want to solve for A. The average distance, in this case, is the name we're giving it, which is a fairly accurate name. All right. We know the period of the moon, we just need to find out how far away it is. Real quick picture, the idea here is that there's the planet Jupiter, and there's some moon an unknown distance away. So that's our value of A. What we know is how long it takes for the moon to complete its orbit. All right, so we definitely know the time, the p-value, all right, is 25 days. But do we need to convert that p-value, right? Do we need more information? In fact, we do, all right? So it's not enough just to know the p-value in days. We actually do need it in seconds, all right? So, that's going to be one of the conversions we have to make when we solve for A. Okay, so let's take note of that. So P is given in those 25 days. How many seconds is that, right? Well, it's not 25 Jupiter days or anything. It is Earth days. We often refer to days in other planets, but it's referring back to Earth days, a common unit of time. So 25 days times 24 hours in a day times 60 seconds in a minute times, 60 minutes an hour times 60 seconds in an hour, or 60 seconds in a minute. Can't keep them straight. Well, then the final unit right there is seconds. So you can see then in 25 days, there is the product of 25 times 24 times 60 times 60. So whatever that number is the number of seconds in 25 days. It'll be a large number. Okay, so that's your value of P. Your value of M is already in the correct units. So you're going to put M right in as kilograms. So 1.898 times 10 to the 27 kilograms. Those are base units, okay? G is also expressed in base units. So you can use it as written, 6.67 times 10 to the negative 11. Whereas the mass is a very big number, the gravitational constant is very small. 4 pi is just a number, right? This is just pi, approximately 3.14. 4 is just a number, so that means that this denominator, since it's 4 times pi squared, which is about 9, because pi is about 3, so it's about 36. So we should expect the numerical value of the denominator to be around 36. Okay? But how do you actually solve for A? Well, you have to actually take the cube root. Now, many calculators have a cube root option, so you can say take the cube root to solve for A. Some calculators do not have a cube root, but they have an alternative. All right. In that case, you'd want to raise everything to the 1/3 power. So a cube root, which is often written like this, so like a square root with a 3 to denote it's a cube root, instead can be written as parentheses to the 1/3 power. Okay, so the idea here, since we are trying to solve for a, is we have a cubed, and we want to take its third root, whether we're taking it like this, writing it as a third root, or whether we're writing it as an exponent of the 1/3, because those are equivalent, okay? In each case, it undoes the cube, and what we get out of this is just a, because of course, that's what we want, all right? When you actually put this in a calculator, especially the 1/3 exponent, you would take your whatever value you want to raise. So we'll have some general expression x, just as a placeholder, and then you're going to raise it usually with this symbol here, and then in parentheses 1/3 power. Okay, so this symbol is used, that's a common symbol in a calculator, as well as if you're using Google, right? You can just type this into a Google search bar. If you're using Desmos, there's something similar, although I think there is actually a value for raising. But when you do the power, make sure that if there's not, you don't separately see that superscript and can clearly tell that you are still in the exponent. Make sure that you put parentheses around it. So on an older calculator, not using something like Desmos, not using something like Google, you definitely want to make sure you have those parentheses. Otherwise, it'll just take x to the 1 power and then divide all that by 3. And that's not what you want. Hence the parentheses around the exponent. Okay? All right. So that would isolate a, but you need to do that to both sides. Because anytime you do something to one side of the equation, you do it to both sides. So the result, if you take the cube root of both sides, so there's a cube root of the side that is, after all, just a cubed, to remind you up there, okay? Well, you'll have to also take the cube root of the other side. Okay, so over here, you'd have gm over 4 pi squared times p squared. Okay, and that's all also going to be in a cube root. That means that now, on the left-hand side, you have what you are seeking. And it is just a matter then to plug it in. Let me rewrite this cube root with the fractional exponent, because this is kind of like you would see it in a calculator. So gm over 4 pi squared times p squared, all raised to the 1/3 power. Okay? And there you go. That will be your value as long as you converted days into seconds and, well, made sure to do the math right. Definitely you want to make sure that you are, in fact, taking the product of numbers like these. So maybe, make sure it's g times m over 4 pi squared. The key here is to use parentheses properly, right? So make sure you're using parentheses when you need to. Make sure you're checking for the reasonableness of your value. This should be some millions of kilometers. It's a rather large distance, all right? And by the way, the last thing to note here is this will give you an answer in meters. So let's just quickly point that out. So because all the units we used are base, we will get answer in meters, which is usually fine, but it's just, if we are talking about orbits and such large distances, it makes sense to convert to kilometers, and that's why I asked for the answer in kilometers. So your last step is convert to kilometers from meters. Okay? All right, well, I hope this video has been helpful for solving the second problem of this week's homework. Thank you so much for watching.